Welcome, fellow explorers, to the fascinating world of calculus. It might sound intimidating at first, but trust me, it's a journey worth taking. Calculus is not just about numbers and equations, it's the language of the universe, describing the ever-changing world around us. From the smallest atom to the largest galaxy, everything in the cosmos is in a state of constant flux. And calculus is the key to understanding these changes. Think about a rocket launching into space. How do scientists predict its trajectory, its velocity at any given moment? Calculus. Or consider the spread of a virus. How do we model its growth and develop effective strategies to combat it? Again, calculus. This incredible tool allows us to unlock the secrets of motion, change, and growth in ways that traditional mathematics simply cannot achieve. So, buckle up, and let's embark on this exciting adventure together. Our first stop takes us to the heart of change itself, differential calculus. This branch of calculus focuses on a fundamental concept called the derivative might sound scary, but it's actually a pretty straightforward idea. It's all about understanding how something changes. Imagine you're driving a car. Your speedometer tells you how fast you're going at that very instant. That's precisely what the derivative tells us in calculus. The instantaneous rate of change of a function. Let's say you're charting the growth of a plant over time. The derivative would tell you how fast the plant is growing at any specific day. But wait, there's more. Derivatives are incredibly useful in a wide range of fields. Engineers use them to design everything from bridges to airplanes, ensuring they can withstand various stresses and strains. Economists use derivatives to analyze market trends and make predictions about stock prices. And physicists use them to describe the motion of particles and the behavior of waves. Now that we've explored the world of instantaneous change, let's shift gears and talk about accumulation, the fascinating realm of integral calculus. This branch of mathematics is all about understanding how quantities add up over time or space. If differential calculus is about breaking things down into infinitesimally small pieces, analyzing the minute details, then integral calculus is about putting those pieces back together to understand the big picture. It's like assembling a puzzle where each piece contributes to the overall image. Imagine you're trying to calculate the area of a strangely shaped lake. This lake isn't a perfect circle or square. It has all these curves and inlets that make it unique. It's not a perfect circle or square. It has all these curves and inlets. Traditional geometry falls short here. Integral calculus to the rescue. By using this powerful tool, we can tackle such complex problems with ease. By dividing the lake into infinitely small rectangles and adding up their areas, we can determine the total area of the lake with remarkable precision. This method allows us to approximate the area as closely as we need. But integral calculus is much more than just calculating areas. It's a versatile tool that helps us understand accumulation in all its forms, from physical spaces to abstract concepts. It's about understanding accumulation in all its forms. For instance, it can help us track the growth of a plant over time, or the accumulation of data points in a study. For example, it allows us to determine the total distance traveled by an object with varying velocity, even if the speed changes at every moment. Calculate the work done by a force, which is crucial in fields like engineering and physics, and even analyze the distribution of heat in a material, which has applications in thermodynamics and material science. And here's the beautiful part. Differential and integral calculus are intimately connected through the fundamental theorem of calculus. This theorem bridges the gap between the two, showing their interdependence. This theorem essentially tells us that differentiation and integration are inverse operations, like addition and subtraction. They complement each other perfectly. It's one of the most important concepts in all of mathematics, and it highlights the elegance and interconnectedness of calculus. This interconnectedness is what makes calculus such a powerful and beautiful tool in understanding the world around us. Beyond the flat Earth multivariable calculus. This branch of mathematics opens up a whole new dimension of understanding. So far, we've explored calculus in a two-dimensional world, dealing with functions of a single variable. This has allowed us to understand rates of change and areas under curves in a simplified context. But the real world is far more complex and fascinating than that. Our environment is inherently three-dimensional, and often, we need to consider multiple factors simultaneously. Enter multivariable calculus, which allows us to extend the principles of calculus to functions of multiple variables. This extension is crucial for modeling and understanding real-world phenomena. Think about a weather map showing temperature variations across a region. Such maps are essential for predicting weather patterns and making informed decisions. The temperature at a particular location depends on both latitude and longitude, making it a function of two variables. This is a simple example of how multivariable calculus can be applied. Multivariable calculus provides the tools to analyze such functions. It helps us understand how changes in one variable affect another, and how they interact. One of the key concepts in multivariable calculus is the gradient, which is a vector that points in the direction of the steepest ascent. Imagine you're hiking up a mountain. The gradient tells you the direction of the steepest ascent at your current location, guiding you to the peak. The gradient not only shows the direction but also the rate of increase, making it a powerful tool in optimization problems. In mathematical terms, the gradient of a function points in the direction of the greatest rate of increase of that function. This concept is widely used in various fields. The applications of multivariable calculus are vast and diverse. It is a cornerstone in many scientific and engineering disciplines. It's used in fluid dynamics to model the flow of air over an airplane wing, helping engineers design more efficient aircraft. In electromagnetism, it describes the behavior of electric and magnetic fields, which is essential for developing new technologies. And in economics, it helps analyze complex systems with multiple interacting variables, providing insights into market behaviors and economic policies. The language of limits and continuity. Underlying the entire edifice of calculus is the language of limits and continuity. These concepts are not just abstract ideas, they are the bedrock upon which much of modern mathematics is built. These concepts are fundamental to understanding how functions behave and making sense of derivatives and integrals. Without a firm grasp of limits and continuity, the deeper aspects of calculus would remain elusive. Imagine you're approaching a wall. This simple analogy helps to illustrate the concept of a limit in a tangible way. As you get closer and closer to the wall, the distance between you and the wall gets smaller and smaller. This shrinking distance is a practical example of how limits work. We can say that the distance approaches zero. In mathematical terms, this is what we mean when we talk about a limit. This is the essence of a limit. It describes the behavior of a function as its input approaches a particular value. Limits help us understand the behavior of functions at points that might be difficult to evaluate directly. Continuity, on the other hand, is all about smoothness. It ensures that a function behaves in a predictable manner without any abrupt changes. A continuous function is like a smooth curve, without any sudden jumps or breaks. This smoothness is crucial for many applications in science and engineering. It ensures that small changes in the input of a function result in small changes in the output, making the function predictable and well-behaved. This predictability is what makes continuous functions so valuable in real-world applications. Limits and continuity provide the rigorous foundation upon which the entire framework of calculus is built. They are the tools that allow mathematicians to explore and understand the infinite complexities of the mathematical world. They allow us to talk about instantaneous rates of change, areas under curves, and the behavior of functions in a precise and meaningful way. Without these concepts, the powerful techniques of calculus would be impossible to apply. Calculus in our world. Calculus is not just an abstract mathematical theory, it's a powerful tool that shapes our world in countless ways. From the smartphones in our pockets to the GPS systems guiding our cars, from the medical imaging technologies that diagnose diseases to the financial models that drive our economies, calculus is everywhere. It allows engineers to design safer and more efficient structures, physicists to unlock the secrets of the universe, and economists to make better decisions about resource allocation. Calculus is the language of innovation, driving progress in fields as diverse as medicine, technology, and environmental science. Conclusion: keep exploring. As we conclude our journey through the world of calculus, I hope you've gained a newfound appreciation for this incredible branch of mathematics. It's not just about memorizing formulas or solving equations. It's about understanding the language of change and using it to unlock the secrets of the universe. But this is just the beginning. There's so much more to explore in the vast and fascinating world of calculus. So, keep asking questions, keep challenging yourself, and most importantly, keep exploring the beauty and power of mathematics. Who knows what amazing discoveries await you on your journey?